Santosh Shivan.
Yes, ma'am. Good morning. Good morning to one and all gathered here. I am very happy to welcome you all, and special welcome to today's speaker, Rajprabhu Thangappa. He is working as a graduate research assistant to pursue his PhD from North Carolina State University, USA. His research is on evaluating the performance of integrated abutment bridges. He earned his bachelor's in civil engineering from NIT Tiruchi 2014. After having worked as a structural engineer, he moved to USA in 2017 to pursue his graduate studies. He worked with Dr. Merlin Kowalski and Dr. Ash Capps on implements of spectrum match of multi-component ground motion on response verification for his master thesis. His research interests spans around performance earthquake engineering and non-linear design of reinforced concrete structure. Very happy to welcome you, sir.
Thank you. Thank you, Dr. Sasikala. Thank
Welcome you,
Santosh
sir.
Shivan. I'm very happy to start my presentation today on force-based seismic design of structures. And I'm very happy to thank my mother, Ms. Thangappa, who gave me this opportunity to present this webinar, and special thanks to Dr. Sasikala for arranging everything. Let's move on. So let me start with a brief overview on earthquakes.
Sir, 1 minute, sir.
Yes.
Participants, kindly mute your audio and stop presenting.
Is everybody able to see my screen?
Yes, sir.
Okay. Can I start?
Yes, sir. You can proceed.
Okay. Let me continue. So we have here the tectonic plates around the globe, which you can see in the figure here. That the Earth is divided into several tectonic plates, and the earthquakes happen because these tectonic plates move as a result of convection currents. And you see here on the bottom are these dots representing the occurrences of earthquakes in the past. So you can see that the earthquakes occur along the fault lines, and the movement of the fault lines result in vibrations underneath the ground, and that has been measured by accelerometers, and this has been possible because of the technological innovations that has taken place over time. Moving on, so to further supplement how earthquakes occur, this slide would help us understand what is the reason behind the movement of the tectonic plates. As we all know, the Earth mantle is liquid, and it can, there are temperature differences between the core of the Earth and the surface, and this causes convection currents to move inside the Earth. And this, because of this convection currents, it 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 causes the Earth's crust to move among itself, and these cause plate boundaries, and subsequently the movement of these plate tectonics happen, and they result in earthquakes. To get into more detail here on the type of the boundaries, you can see the continental. I mean, you can see the rift boundaries when two plate boundaries are moving back away from each other. You can see a rift on the globe, as well as when two plate boundaries are converging, you can see mountains forming. So the Himalayas is a result of the European plate and the Indo-Australian plate moving together, as we can see in the previous slide. Indian plate and the Eurasian plate. Yes?
Sir, the PPT not visible, sir.
PPT not visible?
Yes, sir.
Let me check. Can you see now?
Yes, sir. Yes, sir. No, okay.
But okay. Slideshow is not there, sir.
Yeah, now I just came to the Google Chrome to receive my presentation. I think now it will be fine. Okay, let me continue. So As I was saying, the Indian plate and the Eurasian plate moves. I mean, the Indian plate subducts into the Eurasian plate, and that has resulted in the formation of Himalayas. And you can see, you can state several examples of the geographical features across the globe because of these plate tectonics and their movements. And this results in subsequent earthquakes along those plate boundaries, as you can see in this view. Moving on, there are different fault mechanisms. As you can see, the faults move in different patterns, and they're like divided into 4 different fault zones, like the normal fault, the reverse fault, the lateral strike slip fault, and the yeah. So based on the relative moments of the faults, they have been divided into different names, and based on these different movements, they generate different waves across the globe, and they have been measured appropriately. The figure on the right would help us understand what is an epicenter and a focus of the earthquake. So as the convective currents develop, the strain energy stored inside the fault has to be exceeded, and this results in the release of energy at the focus of the earthquake. And this can be measured using wave mechanisms, which we would see further. So the point exactly above the focus on the perpendicular distance between the focus and a point on the ground is called the epicenter of the earthquake, and the distance between the epicenter and the site would be called as the epicentral distance. So moving on, as I was already saying, the different fault mechanisms would result in different waveforms, and earthquake waves are divided into 4 different categories. They are the primary waves and surface waves, and the primary waves are divided into the body waves and the primary waves and the secondary waves. And these are called the P waves, and these are called the S waves. As you can see, the primary waves are just compression and rarefactions, whereas the secondary waves has a transverse movement along its travel. So when these P waves and S waves reach the surface, they transform into surface waves. They would be called the love waves and the Raleigh waves. So predominantly the structures are affected by these surface waves, as you can see. This would cause catastrophic damage to the structures. As we would see further, in order to measure the velocities, the distances, basically the focal and the epicentral distance, the seismologists use the differences in velocities of P waves and S waves and the relative arrival times. And based on that, you will be able
Excuse
to
me,
measure.
1 minute. Can you adjust your mic voice கொஞ்சம் அப்படியே clear-ஆ இல்லாத மாதிரி இருக்கு. Can you adjust your mic?
Can you hear me now?
I can hear, but கொஞ்சம் குறன்னு இருக்கு.
I don't know what to. ஸ்டார்டிங்ல இருந்தே இப்படிதான் இருக்கா?
ஸ்டார்டிங்ல இருந்தே இப்ப கொஞ்சம் பரவாயில்ல.
Let me do something else. இப்ப கேக்குதா மேம்?
இப்ப கேக்குது.
ஹலோ.
கொஞ்சம் மெதுவா கேக்குது. ஆனா நான் ஃபுல் சவுண்ட் வச்சிருக்கேன், மெதுவா கேக்குது.
ஹலோ. கேக்குதா மேம்?
அதான் கொஞ்சம் சவுண்ட் ரொம்ப லெஸ்ஸா கேக்குது. நான் ஃபுல் சவுண்ட் தான் வச்சிருக்கேன்.
இப்ப ஃபுல்லா கேக்குதா?
இப்ப நல்லா இருக்கு. இப்ப கரெக்டா இருக்கு.
Shall we continue?
Thank you, sir. Yes, sir.
Okay. Shall I continue, ma'am?
Okay, you can continue.
Okay.
So where was I? So I was talking about the wave mechanisms and different forms of waves and how earthquake distances can be measured using the relative differences in velocities and arrival times of these particular waves. So moving on, as structural engineers, we are not interested in how earthquakes arrive or um, how to measure the distances, and these are taken care by seismologists. So when it comes to designing structures, we are interested in what are the direct and indirect effects of an earthquake. So as you can see in the direct effects, it has been divided into ground effects and structural effects. So when you take ground effects, you can see ground shaking, ground cracking, differential ground settlement, soil liquefaction, lateral spreading, landslides, and rock falls. And when it comes to structures, predominantly vibration of structures, falling objects, and structural damage and structural collapse is what we are interested in. So moving on into the presentation, we might not be concentrating on all of these aspects. As you know, the topic of interest is force-based design. We will be, trying to quantify the earthquakes and how these earthquakes would impact the structure would be seen. And we are not that much interested in indirect effects, and these are pretty much placed here just to give a broad perspective on how earthquakes can impact different things. And when we say indirect effects, everybody would know about the tsunamis, landslides, the unwanted floods and fires that would be a result of earthquakes is also of interest. So these are some of the structural collapses which I thought would, be interesting to be seen. On the left, you see is a bridge which has been completely collapsed, and this might be due to inadequate design, probably. On the base of the column, there would have been not enough anchoring of these reinforcements, maybe due to the heavy weight of the structure. This might have happened. On the right, you see is a typical reinforced concrete building in which this failure is because of the soft story effect. You would say is because of the differences in stiffnesses of the building along the height of the structure. So moving on, I would be interested in talking about how to quantify earthquakes. So here we have an acceleration record and a response spectrum and two time histories. So in order to understand or quantify the effect of an earthquake, we would have to solve the second order differential equation for a single degree of freedom system. And a single degree of freedom system can be characterized by a spring mass damper system subjected to a time dependent force. So when you say a time dependent force, it can be related to the time dependent earthquakes. And by using the concepts of structural dynamics, we can solve the second order differential equation mathematically for a period. So so when you have a single degree of freedom system, you can relate the stiffness of the system to a natural period of vibration. So at a particular natural period of vibration, we can solve the second order differential equation to get the acceleration time history response. So in order to construct the response spectrum, we will have to repeat these calculations at several periods in order to get the peak response. So the response spectrum is basically a plot between the spectral acceleration and the natural period of vibration. And This spectral acceleration is basically the maximum response of a single degree of freedom system. So when we have to construct the response spectrum, we will have to repeat the calculations for several natural periods of vibration to get the peak acceleration for the respective single degree of freedoms to construct the response spectrum. And the predominantly response spectrum is plotted for 5% damping, and this damping is taken care by this C, and M is basically the lumped mass of the system. So after having said how to quantify an earthquake, we would have to understand how it has been brought into the design codes. So this has been done using the attenuation models, and so the ground motion attenuation models take care the joint occurrence of earthquake at a particular site. So the ground motion parameter of interest can be expressed as a function of magnitude, rupture distances, and other uncertainties. So as we already discussed how to calculate a response spectrum for a single earthquake record, when we do those calculations for hundreds of earthquake records at a particular site measured using accelerometers, and there has been several organizations record these accelerograms, and they process them further to refine their noises. So as we have these refined accelerograms, we perform the response spectrum analysis for those available ground motion records and perform regression analysis further to relate the ground motion parameter of interest. Here is basically the spectral acceleration. So the spectral acceleration can be related to the magnitude, rupture distances, peak ground acceleration, VS30 basically representing the different forms of soil in the first 30 meters of the profile, rupture distances, and several other site source parameters can be related to the spectral acceleration. So this is a result of regression analysis being performed on a huge amount of data. So this would help us. This would help us in finding these constants, which are period dependent, and these studies have been performed in large numbers, and there have been several reported studies of these ground motion models, and one of them is from Abrahamson and Silva from 2008. So these constants, as you see here, A1, A12, A13, are period dependent. So when you want to calculate the response spectrum of a particular site, you can use these constants which are period dependent to construct this response spectrum for different magnitudes. So this ground motion models would take care of the take care of the past earthquakes that has happened in that particular site, and this is very important to quantify the earthquake occurrence. So moving on, I would talk about the probabilistic seismic hazard analysis, usually called PSHA. So the probabilistic seismic hazard analysis, you make use of the attenuation models, the recurrence laws of magnitude and source to site distances, and it generates a plot between the annual rate of exceedance of an earthquake intensity measure and the spectral and the intensity measure. So the intensity measure taken here is basically the spectral acceleration at the first mode period. So as we saw in the previous slide, the attenuation models give a relationship between the intensity measure of interest and the ground motion parameters. And this is used to find the probability of exceeding an intensity measure given on a magnitude and a rupture distance. And the recurrence laws of magnitude and source distance gives the probability density function of the magnitude and rupture distances, which are used to calculate these two functions. And this is being repeated for the existing fault lines across a particular site, and this results in a site-specific seismic hazard curve for a chosen intensity measure. And the additional output of PSHA would be the magnitude rupture distance de-aggregation. So the de-aggregation is basically a plot between the contribution of the particular earthquake and its rupture distance and magnitude, respectively, plotted along these horizontal axes. And this gives a variation of the earthquakes that has been considered to calculate these hazard curves. And as you know, these hazard curves are plotted across different annual rates of exceedance and different intensity measures. And we would be further using these hazard curves to construct the design spectrum, which we will be using in the design of structures. So moving on, the next step from the probabilistic seismic hazard analysis would be the uniform hazard spectrum. So when I say uniform hazard spectrum, it means that the annual rate of exceedance is uniform across the site. So when most of the design codes are constructed for 2% probability of exceedance in 50 years. So these hazard curves can be constructed for different periods. As I explained previously, the intensity measure chosen here is basically the spectral acceleration at the first mode period. But if we keep changing the period, the attenuation relationship keeps changing based on the period, which we explained before. And this would result in different hazard curves, as you see in this plot. So this is a variation in period. So as the period increases, your spectral acceleration is getting reduced, basically, for a chosen annual rate of exceedance, which is evident in the plot on the right, because as the period increases, the spectral acceleration decreases. These are plotted for different annual rates of exceedance. So moving on, you would be using the uniform hazard spectrum to construct the design spectrum. The plot here shows the comparison between the uniform hazard spectrum and the design spectrum. So you can see that the uniform hazard spectrum is not equivalent to the design spectrum, because when constructing the design spectrum, the codes, they just make use of these hazard maps that is a result of the probabilistic seismic hazard analysis performed at 0.2 seconds and 1 second. So these hazard maps result in specific ground motion values, which smoothens the uniform hazard spectrum. And on the right, you have here is the comparison between the uniform hazard spectrum and the median spectrum predicted by the ground motion models. So moving on, when it comes to India, we have this design spectrum in IS 1893, and this is based on the different types of soil. So I would say these advanced studies which we discussed earlier has not been yet implemented in India because of the because we need site-specific seismic hazard analysis to and we need a lot of data analysis. So that's why we have the impact of soil in these graphs. But when you see the AAC 7 maximum considered earthquake spectrum, the impact of soil is already inbuilt in the attenuation models. So based on a particular, based on the probability of occurrence of earthquakes at a particular site, the impact of different soils has been already taken into account. So let's get into the force space design operation sequence. And whatever we have seen until now is to basically quantify the earthquake demand. But once we have quantified the earthquake demand, we will have to quantify the earthquake, I mean the structure capacity to design for the actual earthquakes. So this would be the step-by-step procedure, I would say. The first step is to estimate the structural dimensions based on gravity load design and the member stiffnesses. And after that, we would have to estimate the natural period. This can be performed by either eigenvalue analysis or from simplistic Gödel equations. And there are several methods to obtain natural periods. You can model the system in a software, and these softwares give out the natural periods of vibration, which we can use in our subsequent analysis. And once we get the natural period of vibration, we get the elastic forces from the acceleration spectrum. So as we have seen earlier, the designed spectrum is basically the relation between the spectral acceleration and the period. So once we have the natural period of vibration, we can get the spectral acceleration pertaining to the natural period of vibration, and from that we can calculate the elastic forces. And once we determine the elastic forces, we will have to select the ductility level and the force reduction factor. Moving on, we calculate the seismic forces, analyze the structure under seismic forces. This would be done by a structural analysis software, either STAD or SAP would work. And moving on, we would design the plastic hinge locations. And if the displacement measured are within the limits, we would continue to perform the capacity design for shear and non-hinge moments. And if it is not okay, then we would revise the stiffness, and that would ultimately change the fundamental period of vibration, which would impact all the other design steps. So there are more complications involved in estimating the ductility and the force reduction factor, and there has been numerous research behind the relationship between the ductility level and the force reduction factors, which is out of scope of this talk. Plastic hinge locations, deciding them is a separate task in itself. And the capacity design for shear is in itself a detailed analysis. So moving on, I thought of giving an illustrative example for a force space design using equivalent lateral force method. So here we have a G+8 building, which is with each story of 2.7 meters and the bay length of 8 meters. And this is a square building of 16 meters. So we would have to use the force space design approaches which we discussed earlier to design the beams and columns of the particular 2D frame. So the elevation which you can see here is basically the frames on either sides. So when the earthquake happens in the lateral direction, these frames, these beams and columns would bend laterally, would basically sway. And we will be seeing how to design the beams and columns for the earthquake forces using equivalent lateral force method. So this design is based on the design spectrum from ACE7, but you can replicate this procedure by just replacing this design spectrum using the design spectrum from Indian code. So when I say the seismic hazard, it is dependent on the site. So each each site would have its own seismic design curves based on the codal values. So moving on, these are the member properties and the natural period calculations. On the left, you see here is the properties of the beam. The beams are all assumed to be 400 mm by 600 mm. The columns are assumed to be 800 by 800 mm. And the values you see here are basically the locations of the reinforcements for the beams and columns respectively. And we have chosen 16 mm diameter bars and a reinforcement ratio of 0.75% would result in these pattern of reinforcement. And the distance you see here is basically from the edge of the beam. So the depth of the beam is 600 mm and the distance is 58, 300 and 542 represent the location of the reinforcement from the respective ends. And as you see here, for the columns, we have chosen 24 mm diameter. And based on 1% minimum reinforcement, we have calculated the number of bars and its location respectively with respect to the height of the section. So this would be useful in moving on further. But for now, we are just defining the cross section and the reinforcements. So this you can assume to be, the outcome of the gravity loading, basically dead load, live load, and yeah, pretty much that. And once you perform structural analysis for that and do design calculations, you would end up with the reinforcement pattern. But we are not going into that. But if you are doing a real project, you can do that. But we are just assuming the reinforcement patterns based on the minimum percentages of reinforcement. So moving on, we are not calculating the fundamental period based on eigenvalue analysis. Rather, we are using a simplified codal equation to find out the natural period of vibration. So this is the period of vibration is related to the height of the structure. And as we know, the height is 24.3 meters. It's basically 2.7 times 9 because it's a G plus 8 building. And we have a moment resisting frame. And these equations are taken from ACE 702. And it results in a natural period of vibration of 0.78 seconds. So moving on, once we have the natural period of vibration, the subsequent step is to estimate the spectral acceleration. And once we estimate the spectral acceleration, we can estimate the seismic base shear, which is dependent on the seismic coefficient times the weight of the structure. And the assumption is that each floor has a weight of 2000 kilonewtons, and that times 9 would give 18,000 kilonewtons. So that would be the total weight of the structure times the seismic coefficient, which is represented by these two formulas. SDS and ST1 are basically the spectral design values for short period and 1 second. And as I previously told, those hazard maps are for 0.2 seconds and 1 second. So SDS would be the hazard value for 0.2 seconds, and ST1 would be the hazard value for 1 second, and these are represented in the code. So moving on, we have the SDS and ST1 values, and the period of vibration is 0.78, and we have to use the force reduction factor to reduce the forces. So usually we design structures for reduced force, trusting its ductility. So the ductility is representing the ability of the systems to deform without loss of strength. So there is a direct correlation between ductility of a system and the force reduction factor. So for moment resisting frames, you would have a value of 8, unlike if you use a maybe a simple moment resisting frame, then it might reduce to 5. But and in case of if you use a masonry structure, then it might even reduce to 2 or 3. So moving on from the earthquake hazard and the natural period of vibration, we have I can hear some noise, Dr. Sasikala.
Sir,
Yeah, I could hear some.
It's clear. Participants, please mute your audio.
Yeah, now it's fine.
Please, you can proceed.
Okay. Yeah, now it's good. So we calculate the seismic base shear, and from the seismic base shear, uh, we can calculate the vertical distribution of seismic forces across the height of the building using this formula. So these are all codal provisions, and there are similar codal provisions available in India where for equal and tidal forces, they relate the base shear with the force coefficient represented by the weight and the height. And there's a factor K, which is there is a factor K which is dependent on the period of the structure, and since our period is 0.78 seconds, which is between 0.5 and which is between which is between 0.5 and 1 second, we have K values interpolated between 1 and 2.5, that would result in 1.14. We further use this to calculate the story forces across the height of the structure. So here you have the weight, 2000 kilonewton, assumed across all the stories, and here you have the respective heights of each story, and then you multiply these two to get this factor, and you sum them and divide each of these values with this value, you might get this factor. And using these factors, you multiply with the seismic base shear, you'd get the respective forces, which would be the equivalent lateral force acting on the system. So this is how the dynamic effect of the earthquake is, considered to be equivalent lateral forces acting on the system. So once we determine the equivalent lateral forces, then we can apply these lateral forces onto the system and perform structural analysis to perform structural analysis to design the system subsequently. So once we find these seismic forces, since we have two frames, we divide these seismic lateral forces by two to apply them on a 2D frame. So we have these respective forces at the floor levels, and the highest being at the top. And as you see, this would result in a triangular variation of forces applied laterally onto the building. So this would result in this particular pattern of bending moments and shear forces, and this is typical of any lateral load analysis where the column moments keep on reducing as you go from the base to the top, and similarly the beam the beam moments, there would be beam bending moments because of the lateral sway of the system. So we further use these maximum bending moments to, verify the member stiffnesses. So this is done because in order to perform the structural analysis, we will have to, assume the stiffnesses of beams and columns, and it is generally not advisable to, uh, you know, model these stiffnesses as cross stiffnesses. So we have the area of the beam, we have the geometric properties of the column as well, and usually we used to assume 0.2 times the cross section stiffness of the beam for modeling purposes, and 0.5 times the gross moment of inertia for the column to model the beams and columns. And as you know, as we change the stiffnesses of these beams and columns, the moment demands at the ends of the members changes because as you know, the stiffnesses would impact how much force a member can take. So we will have to verify whether the assumed member stiffness and the calculated member stiffness are kind of similar. So for this, we will have to divide the columns and beams into 3 groups. So we have 9 stories. So the first group is basically the first 3 stories, and subsequently the second 3 stories and the last 3 stories. So here you have the columns and beams, and these are the bending moments, maximum bending moments in the respective groups in the column and the beam. So once we have the bending moment, and we can estimate the crack section stiffness using this relation. As you know, the moment, the Young's modulus of reinforced concrete, and the yield curvature is basically represented by the so the yield curvature is the relation is represented by the yield strain and the depth of the section. So we have all these parameters, and once we know the moment, we can calculate the crack section stiffness, and we can compare it with the assumed stiffness. So you can see here that the assumed stiffness is much higher than the actual stiffness. So the actual stiffness is basically based on the moment demand, which is a result of the application of lateral loads. So there is a discrepancy between the assumed stiffness and the actual stiffness from the demands. So there is a need to reiterate the analysis to match the assumed and the actual. So this is repeated for the second group and the third group, and you can see the variation in the assumed and the actual values for these respective groups in the columns and beams. So moving on further, we would have to also check the crack section stiffness for minimum reinforcement in the beams and columns. So as we already discussed, this will be the reinforcement pattern for the beam, and using some available softwares, we can perform the moment curvature analysis, and this would give us the yield moment and the yield curvature or for a particular cross section with a defined reinforcement pattern. So once we determine the yield moment and the yield curvature, we can use the similar relationship to calculate the crack section stiffness. So we would have to make sure that the crack section stiffnesses which we get from the minimum reinforcement should be, should be, this should be the minimum value that should be adopted. So when you move to the previous slide, you have in the beams the assumed values based on zero 0.2 times the cross moment of inertia. So you can observe that you can observe that the crack section stiffness is less than the assumed value. So we would have to use the reduced value, but it should not be less than the value pertaining to the minimum reinforcement. As you see here for the third group, the crack section stiffness from the moment demand is 0.001, but for the minimum reinforcement it's 0.00114. So instead of using 0.001 in the subsequent analysis, we will be using 0.00114 based on the minimum reinforcement. But on the other hand, for the second and the first group, the crack section stiffnesses from the moment demands are slightly greater than 0.00114. So that would result in using the actual values from the moment demands. So moving on, we will have to repeat this process for the columns, and estimating the crack section stiffness from the moment curvature analysis. We decide the new crack moment of inertias that we will be using in the subsequent analysis. Once we have the developed stiffnesses for the beams and columns based on three groups, we apply the same lateral forces which we calculated earlier to get new moment demands. And subsequently, we will have to verify the stiffnesses are matching, and it should match because we have defined this analysis. So moving on, we will have to find the displaced shape, and this displaced shape is an outcome of structural analysis, and you can obtain these displacements along the height of the building from the software analysis outputs. And using the Rayleigh method, we can estimate the natural period of vibration of the structure. So as you saw earlier, we used the simplified Odell equations to estimate the period, but we can also use some detailed analysis techniques to estimate the period based on the displaced shape. And as you go through this process, this is almost similar to calculating the lateral forces. So you have these parameters defined here, and basically the story weighs 1,000 because we are just analyzing for one 2D frame, unlike the entire structure. And we have the respective heights, and we have these respective displacements as an output of the structural analysis, and we have these respective forces which we apply at the respective stories. And once we have all these values, we can estimate these numbers and arrive at the period. And you can see that the period is 2.67 seconds, which is much different from the 0.78 seconds. So at this stage, what we should do is, perform the calculations again, because once the period changes, the lateral forces which we will be calculating is going to change, and that would result in different displacements, and that would result in different period. So we will have to perform the iteration to match the period of the structure, so that we would so in this process we would have to change the beam cross section and the column cross section and the reinforcement patterns. So this is how the design process works, and once we converge the period, we would be having the structural design. And one more complication I have not considered in this entire process is during the structural analysis, we have not considered the effect.
Participants, kindly mute your audio.
Yeah, there's too much noise. Yeah, now it's clear. Yeah, so since I have not considered the complications of including the dead load and live load along with the lateral load analysis, if we can do that, then we can result in accurate design. Think of replicating this procedure for a complicated structure, and mostly in reality we might not have the symmetrical frames, and there would be additional complications in the way forces are transferred, and we would have to apply this procedure on different directions of the building and consider the critical forces which to decide on the respective design cross sections. Moving on, the final step would be to check for the allowable displacements. So once we have these, once we converge the period based on the displacements, we would have the final displaced shape of the structure, and we will have to amplify this displacement based on a factor. So this is done because of the correlation between the ductility and the force reduction factor. So since we reduce the forces by a factor of 5, by a factor of 8, we would also have to increase the displacements by some factor. Although this is not equal to 8, there are some serious discussions behind how these numbers are arrived, and going into that would be out of scope, but we would have to increase the design displacements and check with the allowable values. So these are the converged displacements, and this would be the increased displacement based on the factor 5.5, and these are the heights. And so we calculate the drift ratio. So the drift ratio would be the difference in displacement between the stories upon the height of the story. So we calculate the drift ratios and compare it with the allowable drift. And you can see all so you can see the allowable values are exceeded. This is because, as I told, we have not performed this refined analysis to match the period. And if we can do that, then we can also, and even after doing that, if we have these drift displacements exceeding the allowable, then we will have to change the member stiffnesses again to satisfy this criteria. So this would have given us an idea of the steps involved in force-based design, and I would conclude by saying the design community is moving towards the displacement-based design rather than basing the displacement on forces. They have the allowable displacements and calculate the member strengths based on different performance limits. So that has been the state of the art, and the design community and the research community is moving towards that. But talking about that would be out of scope for this presentation, as this is based on force-based design. I thought I would give a round tour of how to use this equivalent lateral force method. And also I would like to add, there is so much more than what I have covered, and there is response spectrum analysis, there is time history analysis for design verification, which is again some other concepts at high level, which can be discussed later. So I would like to acknowledge Dr. Movin Kowalski. He's a professor at North Carolina State University, and he's an expert in earthquake structural engineering. And his book on displacement-based design, actually criticizes the force-based design. But yeah, moving on, I would also acknowledge Mustafa for the illustrative example which I presented. And I also acknowledge the graphics which I obtained from the Google search. Thank you.
Participants, any questions? Participants? Sir, you can see the chat section. They are asking questions there. Participants?
Yeah, I can see, Mama.
Sir, I'm Gangai Mani.
Hi, sir. How are you?
Sir. Very fine, sir. Exactly. Lecture is very interesting and also very useful for our students and also me. Sir, only one doubt, sir.
Yes,
it's
sir.
not a question. I need to clear my doubt, sir. So, even though the mostly Japan and related and the region in around of Japan and Indonesia, this region only mostly affected in the seismic zones. What type of the designs, what type of the materials should adopted in the particularly in the Japan constructions? Even though the Japan constructions, most of the buildings, tall buildings also constructed, but their building not affected in the even though higher seismic waves also, even though Richter scale in 7 or 7 and above. But the building is not affected. What type of the designs they are adapted, sir? That's my.
Yeah, accordingly, from what I know, in Japan, there is they use the. I can hear so much noise. I don't know what's happening. Hello.
Yes, sir. Yes, sir. I mean.
Participant, mute your audio.
Can you hear me clearly? I can hear too much.
Yes, sir. We can hear clearly, sir.
Okay. So, from what I know, in Japan they use these seismic-based isolators. So the design is predominantly elastic design, and these base isolations provided, don't allow the earthquake forces to be transmitted to the building. That's how I think they are able to, design systems for very high earthquakes.
Okay, sir. Okay, sir. Thank you, sir. Thank you.
Thank you.
Thank you.
Participants, any other questions? Okay, sir. Thank you. The session was very informative.
Thank you,
I would like to thank Vairakanna madam for arranging this. Thank you, madam. I invite Deepa to say vote of thanks. Deepa?
Yes, ma'am.
Yes.
Good morning, everyone. This is Deepa. First of all, it's my privilege to have been asked to propose vote of thanks. First, I thank today's chief guest for this informative webinar. Thank you so much, sir. Next, I thank my college management and faculty members and our department HOD, ma'am, Dr. Shasikala, for giving us this wonderful opportunity. And finally, I thank all the participants for your active participation. Thank you so much. Thank you all.
Thank you, sir. Your lecture is our 10th lecture in this webinar series. Thank you. Thank you, sir. We had a wonderful session. Thank you, sir.
I had a great time too. Thank you.
Thank you. Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Thank you all. Thank you all for listening to. And if you have any questions, I am leaving my email ID in the chat box.
Okay, sir.
People can I mean, if anyone is interested to talk more, we can chat through email.
Okay, thank you, sir.
Thank you.
Thank you, sir.
Can I end the meeting?
Yes, yes.
Yes, sir.
Thank you. See you.
Thank you.